Hi, and welcome to the Vintage Computer Federation YouTube channel. Your support helps us with creating videos just like this one and restoring vintage computers for all the world to enjoy. So please like, share, and subscribe. Thank you. I want to thank everyone for coming to see Johan talk about reverse engineering the Commodore 128. I know I will be making sure Bill Hurd watches this video when we put it up on YouTube, so be nice to hear what he says about it all. Once again, thank you, Johan, for joining us virtually. We're going to try and have a Q&A session towards the end. If I'm not back, Albert will help out here doing the Q&A session. And that's pretty much it. I think you can see the audience. We did set up a camera, so we're trying to do this interactive. So that helps a lot. And, without further ado, I see some more people coming on in. Johan, take it away.
Yeah, oh, hi. So, my name is Johan Grip. And I've been spending the last 3.5 years reverse engineering the Commodore 128. Or as I usually call it, how to find every single rabbit hole you can find and jump into it head first. So, who am I and why am I talking to you? Well, I'm a computer and electronics nerd, like I guess many of us. I'm entirely self-taught. I have no formal education on any of these topics. I've been working enterprise IT for pretty much my entire career, doing network engineering, database administration, systems, etc., etc., etc. The big background behind this entire project and working on the Commodore 128 is I still have my first computer. I got it on my 10th birthday in 1985, and I've been dragging it along as I've been moving houses in countries, etc., etc. At one point, I started getting a bit interested in actually getting into the whole 8-bit scene again. So I unpacked it, plugged it in, turned it on, and I got a black screen, as you do with most old Commodores. So started working on repairing it, and eventually I discovered that there were some corroded traces on the PCB, which were causing my issues. All the chips were actually still working, but there were some traces that were badly damaged simply from corrosion. And I've not been storing this outdoors in a shack or something like this. It's always been indoors in a box or something. So I kind of figured that if I have these problems, there's probably going to be more of these machines that have these issues. After all, they are 35 going on 40. So at the same time, I was also starting to get involved in some other projects. So first one being the Amiga project by Johan Hertel over in Sweden, who's reverse engineered the circuit boards of the Amiga 1200 and the Amiga 3000 so far, I think. And he in turn has inspired a bloke in the UK named Rob Taylor, who's the man behind the 60 clone boards, the Vicky 20s, and the A500++ recreation PCBs. He's done a lot more. He has a replica of the 1541. He's done some Amstrad machines. He's doing a lot of PCB replicas, which is pretty fantastic. I started getting involved and interested in this, so I kind of, after a while, started thinking that, hey, I can do the Commodore 128, right? So, having learned from previous projects, I decided to set some goals before I started, and the primary goal was that I wanted to preserve the Commodore 128 as a platform, not trying to invent something completely new. So the primary goal was a one-to-one replica of the printed circuit board, but I also wanted to integrate the small factory fixes. Most of the Commodore 128 boards had traces cut, resistors soldered on the underside, bodge wires here and there, not just the infamous bodge wire that Bill Hurd likes to talk about, but there's also other ones. We will go over those a bit more in detail later on. And integrate some of the small quality of life fixes that you generally end up wanting to do. So, John and Rob have been using a small German software called Sprint Layout. Sprint Layout is pretty fantastic in that it allows you to load a bitmap image as a background in the PCB editor. So that makes it very convenient for replicating circuit boards. The downside with Sprint is, of course, it's purely a PCB editor. It doesn't do schematic captures. You have to configure all the nets manually. It gets pretty involved if you want to make any changes to things. The other thing I wanted to make sure for me as a goal is if my board design is going to be open source, which was always the goal, I also want the software to be open source. So, because if I had made it in Eagle or Altium or one of these great softwares, you'd always have that bit of a threshold. I can get the actual design files, but now I need to spend money to actually do something with it. So I decided to use KiCad because I've used it for a couple of smaller projects in advance, or before this, and I'm getting fairly used to it. And on top of that, it's KiCad 6, which is the current version, is getting really good, actually, for most of these type of topics. So, first step was to capture all of the Commodore schematics. They are for the Commodore 128, they are very, very accurate. No real issues involved in them. There was, I think the biggest actual discrepancy I've seen or error in the schematic itself is a missing inverter ring on a 7406 on the output. And there were a few minor discrepancies compared to the PCB. I always use the PCB the PCB is the working machine, so you trust the PCB more than you trust a schematic printed in the reference manual, for example. Case in point, I mean, the schematics were pretty accurate. The bill of material in the programmer's reference guide is mostly accurate, but quite a bit off in certain places. So one has to be a bit careful with that as well. I also did not try to preserve the actual schematic layout. It's 4 pages on the original schematic. It's pretty packed and very condensed in certain areas as things have been evolved over time. There's one section for handling the read-write and bus arbitration between the Z80 and the 8502 CPUs that gets really packed up on the original schematic. So I'd rather break it out. So I did my first attempt, and as you can probably tell, it's a bit of a mess. This was my actual first large project I did in KiCad beyond the usual connect an Arduino to a couple of things. So I was learning as I was going. So in this first attempt, I was using hierarchical schematics, which is a nice setup that KiCad has for dealing with larger setups. But I was also bringing every single trace, every signal onto everywhere. So every single trace on the entire schematic was represented everywhere. Obviously, today we have labels. We tend to use labels a lot more when doing schematics. So I've since gone over and cleaned it up quite a bit and tried to make it actually be the overview schematic sheet to be functional as a block diagram as well. Being quite a bit of work, but it's actually working. I have no errors or warnings in doing the design validations, so It's worked out pretty well. Once you have the schematic captured, of course, you need to, or want to, do the PCB. So that's where the real work starts, right? So I took a board out of a working machine. I ended up sacrificing it. One of the reasons I did that is it allows me to also desolder all the components on it and make a new BOM based on a functioning PCB. So every component I desoldered, I inspected for colorings on resistors and markings on capacitors, etc. Measured them to make sure they matched the numbers, and then brought it down to create that bill of materials to make sure that what I'm actually recreating matches a working PCB. Due to the way that KiCad works, we'll go into that later on, I ended up sanding off the solder mask of the board, done by hand, just using sandpaper and a piece of cork. And then I stuck it in the flatbed scanner at work, which has a nice, shiny, large flatbed scanner in the multifunction printers. The PCB is really large, so I needed a large scanner. So, to prepare this to be done in KiCad, you have to turn it into a monochrome image, because it needs to be converted into a component for KiCad to use. And components are monochrome, so I needed to do that. You also have to align the rotation, otherwise it will not end up nice. I got that mostly correct. You add these two, you do that for the top side and for the bottom side, which is quite a bit of work, especially as I'm a complete moron when it comes to editing graphics and photo management, etc. So it was quite a struggle for me to convert it down to monochrome without getting something that was entirely messy or lost data. So that took me nearly a week to get entirely correct. I'm sure people used to photo editing will do it a lot faster than me, but that's the way it is. Things we learn. So once you have it in KiCad, you see the traces on there. You have the faint green vertical lines, that would be the bottom side, and the faint, well, I would call them turquoise maybe, horizontal lines, that would be the top layer. So you then import all of the components from the schematic, and you place out the components by looking at the PCB, looking at the holes that you have, so the vias and the mounting holes that you have on the imported images. Place out the components. One mistake I did at this stage was I should have located all of these components on a fixed grid. What I did was entirely slavishly followed the original, which meant that at some places I ended up having clearance issues with the traces and a lot of manual work to clean it up afterwards. Once you have that done, you sit down and you draw out all of the traces on the PCB. There's quite a lot of them, so bring patience. A lot of patience. So this is a zoom in on one section of the PCB. It's a large PCB and it is very dense with traces. I mean, this is an old parallel design. There's no nice shiny I2C buses on here. It's all parallel 16-bit address bus. Well, there's a main 16-bit address bus. There are two 8-bit translated upper bytes of that address bus, an 8-bit data bus, and a mess of control lines that you need to deal with. So, as you can see from the numbers down in the corner, there's 14,430 track segments on this board. So those are the individual segments of the track, and I pretty much clicked every single one of those, at least once. Doing this took me 3 to 4 months, I would say. Mostly working on in afternoons and evenings and a bit on the weekends, etc. And the thing that kind of half scares me is the Commodore team did this PCB board layout in 1 week. They were working 24/7 with 3 layout guys, so Terry Fisher, Paul Rubino, and Claude Guy, who were doing all of the layout, and they had Bill Hurd in the room as a technical reference. And Bill used to say that he slept under the table and they would kick him to ask him questions. But they did this in 1 week. I took 3 months and I just copied their layout. They had to actually decide where the components needed to go and follow all the constraints and come up with a functioning board, which is just immense. I can totally understand the RIP comment on the underside of the board. So once I had that done, you find a manufacturing house that wants to manufacture one of these boards. They're 16 by 10 inches. ATX boards are actually smaller than this main board. It's completely packed. If I wanted to stick another 7400 series logic chip on here, I would be in trouble. There is almost no space anywhere on this board that is not packed with traces. So I received my prototype boards back. This was the first revision. Spent 2.5 days soldering one of these up. Since then, I now have it down to about 6 hours from start to finish to solder one of these up. Probably done about 10 at this point, so gotten a bit of a routine on it. Made a few mistakes on this one. There's no mounting holes. I forgot them in my joy of having actually finished dragging out all of those traces. I messed up the footprints on the RF modulator and the RF cage around the video section. I then made a second prototype board to try and fix those before I realized that it's probably a lot cheaper to just print those footprints 1-to-1 scale on paper to verify the footprints rather than making PCBs for it. Things we learn. So, anyways, I got it soldered all soldered up. I messed up the footprint of the video DIN, which is why there's a whole bunch of cables sticking out there instead. Plugged in the power, turned it on, and it worked. It powered on, straight up, first time. Except, it was a bit of a mix-up between upper and lowercase letters all over the screen. I was banging my head on the desk trying to figure out why. Eventually, I realized the board, if you look, there's a small carrier board down in the bottom leftish side with an EEPROM on it. This is an international Commodore 128, so in this case I'm using the Swedish character ROM. The original character ROM is a 2364, which does not follow the same JEDEC pinouts as the larger EEPROMs, the 2764s, etc. So what happened was, when they shipped these out to Sweden to get sold, the Swedish Commodore division remade them into Swedish Commodore, so they were programming EEPROMs to stick into the kernel ROM for the Swedish keyboard layout and the Swedish character. So they made a slimline adapter board, and the thing with this adapter board is they cannot pass A11 straight through, so there's a small cable from the adapter board down to one of the chips next to it, which has to be mounted to do A11. So since I had forgotten to connect this wire, which left A11 floating, and interestingly enough, A11 is the exact one that selects between the uppercase and the lowercase banks in the character. Since it was floating, it was probably picking up the data from one of the address lines next to it, and that's what's caused this upper lowercase mix on the screen. It was a rather interesting failure, but the computer worked. As soon as I plugged that cable in, it was just 100% perfect. I ran a lot of test batteries, and it was just humming along perfectly fine. I was genuinely surprised how well that went. So, moving on to those small factory fixes that I integrated, the first one that we run into is a resistor called R102. It's sitting on the 1 megahertz clock and basically splits the 1 meg clock in two sections. One half going to the lower and the right side of the board, and the other half going up to the VDC and a few other chips up in that corner in the top left-hand side. It's a very low resistance, 68 ohms, I think, and I discussed this with Bill Hurd, and he basically said that it's there to absorb some reflections to make the clock cleaner to some of the chips. So, of course, I didn't want to cut traces and have you guys cut traces and solder a resistor on the underside of a new board. So, with a bit of jiggery pokery, I managed to free up some space and integrate that as a footprint on the PCB instead, which makes it a lot cleaner. The other thing is, and this is one of the differences, and also the reason why you cannot use Commodore 128 DCR, so the metal D model ROMs on a wedge 128. The 128 DCR, so the metal D, has 2 ROMs instead of 4, so that's rather convenient. There are jumpers on the board, J4, J6, and J3, which you can configure to enable you to use the larger ROMs even on a wedge. But due to an error somewhere along the path, A14 was pulled out for the kernel instead of A15. And this was the case in the schematic and on the PCB. So this has not been fixed on the boards I've sold so far, so you still have to budget a bit to use DCR ROMs. It's fixed on the latest revision that will be out shortly. I did, before I fully understood this issue, I made a specific board revision that had a jumper that you could select between A14 and A15. Of course, the computer would never actually work with A14. But that board revision was never stable. It turned metastable and it would run fine for an hour and then crash. Certain demos will just trigger it to insta-crash, and it was all due to that extra bit of tracing on those address lines. It's, in some areas, the board can go really marginal. It's an interesting challenge. It's a large board, and those address lines are going all over the place. So I'm not surprised that if you make any substantial changes to them, things start having issues. But on the latest revision, I just swapped A14 for A15. You can use the jumper. It works perfectly fine and is stable. Whenever I do a new board revision, I solder one up and I run test batteries for days just to make sure that it's fully stable and works. Another fix that I did, which is rather interesting, is J7, which is in the schematic. It's designed so that you can select between the 2 fonts. So on a US Commodore 128, it has one font for 128 mode and a different font for Commodore 64 mode. There's a compatibility reason behind that. Bill Hurd told the story where the QA department came running in and saying they found an issue, and when they started Koala Paint, the computer would hang doing things for minutes, because Koala Paint was drawing its logo by enlarging the built-in font to type text paint, and it would then paint it with a built-in flood paint algorithm. And the dot on the eye had moved position, and the flood paint missed, so it just flood filled the entire screen, which takes forever, of course. So to fix that, they put both the C64 font in the ROM and the 128 font, and it will change which font is active based on which mode the computer is in at the moment. On the international machines, they flipped this around, and you use the caps lock key on the keyboard, which is labeled ASCII DIN on those, to change between the two fonts. So you would have a nationalized font in one and the US font in the other one. This is drawn correctly in the schematic, but it was never put on the PCB. So if you look at the J7 jumper on the image there, one of the pads is not connected at all. There's no connection to it, so it would not work even if you tried. So I managed to fix that as well. So J7 now works. You have to install the jumper, and you can select which mode you want it to be in. Bill Hurd says he has no memory of this being attempted to make international, which makes it a bit curious, seeing as it is in the schematic. So I guess that's one of those items that was lost in the mist of time, I guess. Moving on, this is one of the other small differences in the schematic, and a set of bodge wires on the other side of the board. When they moved to revision 7 on the schematic, they added a driver gate on the read-write line to basically make the read-write signal get to the VDC chip before it gets anywhere else on the board. So the line marked FRW is only connected on the VDC chip, so the 80-column chip. And the read-write line that's behind U57 goes to the rest of the system. I thought it was once again just a way of splitting the lines to not have to run the read-write line across the entire system. I discussed it with Bill, and he said, yeah, we did that to make sure the VDC chip gets the signal before anybody else, probably to make it slightly more stable. The VDC chip runs in its own clock domain for various reasons, so talking to it can always be a bit interesting. It lives in its own little time domain and does its own little things. I guess this gate fix resolved this to some degree. Those are the factory bodges that were done on the board, which ended up fairly all right. There's no need on any of the reproduction boards to do any cutting and bodge wiring, which is nice. And even more amazing to me is, so far there's only been one issue found on the boards, which is I screwed up a resistor. So the green one on the left is an original board, and the red one on the right is one of my recreated boards. That resistor is for the dot clock going to the expansion port. I had it reported by a user who was trying to use a cartridge that needed a dot clock and it wasn't working. We looked into it, or he looked into it, and figured out that this resistor was missing. And I posted about it, and it's been fixed on the current boards. But so far, this is the only issue we've found on these boards, which is fairly nice, actually. It's been really nice. I'm surprised with how well it's all been working out. For the last year or so, I've been working on a new revision that will have a lot more small convenience fixes. One of the big ones, for example, being there's an RF modulator replacement on board, so you can just mount the components where the RF modulator would normally sit. It replaces the RF modulator and just does the mixing to get super video and composite out of the DIN, which saves you having to buy one of the replacement boards. You can just do it straight on the board. I put some ground guard traces around the Luma Chroma, the Luma Sync and the Chroma signals from the VIC chip up to that RF modulator, because the path it takes under the VIC chip really goes very close to clock signals and IRQ signals and dot clocks and AACs and all sorts of noisy signals. And I kind of figured it won't hurt me to put guard traces on there to basically try and protect the video signals a bit. It won't stop working and it might make it better, so I put them on there. When I soldered up the first prototype and turned it on, I was amazed by the level of difference that it made. This revision of the board has almost no discernible jail bars at all. It has one of the nicest video outputs I've seen from an 8-bit Commodore, in my experience. It's really, really nice on the output. There is some faint traces of jail bars still present. I don't think there's anything we can do about that on the PCB, or even if I were to run coax straight from the video chip pins. I think those are basically caused by the simple fact that the video output lines on the video chip is right next to the 1 megahertz clock and the AAC arbitration signal and other noisy signals. So the remaining jail bars and noise on those video lines, I'm pretty certain comes from within the VIC chip. So not something that you could really be able to easily fix on the PCB. Other things I have done on this revision is I put out pin headers for the address bus. In total, I have pin headers for the unused I/O decodes, so D5XX and D7XX. They're readily available as pin headers, so no need to solder wires, etc. And some other of the signals that you might want to look into: AAC, BA, IRQ, IO1, IO2, etc. All of the things you might need to run dual SIDs and what have you. Certainly a lot nicer option to have an actual pin header than running grabber cables. I've also put in jumpers to allow you to do bank selection on many of the ROMs, especially the kernel ROM and the function ROM. So no need to put you can just put in a 27C512 in those sockets and you will be able to use all of the banks in that EEPROM straight on the PCB, either with jumpers or just running out the switch as you want. So I'm expecting to receive the final prototypes next week, and they will be going on sale shortly thereafter, once they're validated. I put connectors in for the spare pin on the audio video DIN. If you want to run dual SIDs, you have that connected right there. There's a jumper to ground the audio in pin to reduce noise. All of these tiny little things that just makes life nicer. So I'm really pleased with this new revision. It's coming in together all night. Going back to the softwares, there's a really nice feature coming in KiCad 7, which is bitmap backgrounds, which will allow you to do what you do in Sprint, but now in KiCad. So it's available in the nightlies right now. I've been using it a bit. I haven't put anything large in there yet because KiCad 7 is not fully stable. KiCad has moved to yearly releases, so it should be coming out late this year, early next year. That's the current planning. And that's an absolutely fantastic feature. It will be really nice to have in there for this type of work. Also, since I apparently have a bit too much spare time, I managed to find a not very common version of the Commodore 128 called the 128CR. So it's not the DCR, the D model. This was a cost-reduced version of the board for the normal wedge machines. We suspect there might be a few thousand of these out there, but they're not very common indeed. As you can tell from the board, it has a very different layout. If you're used to looking at the 128, this board has a vastly different layout. It's based on the 128 DCR circuit board, so it has only 4 RAM chips, so and a very different layout. 2 ROM chips, 4 RAM chips. It has the 64K VDC DRAM, and it's a fairly nice layout. For some reason, they made the PCB slightly smaller. As you can see, the mounting holes do not line up, especially if you look in the top right corner there. And the way they mounted these into the cases was they use these brass melt inserts into the case. So if you ever see a 128 with brass inserts melted into the case on the underside, it's going to be one of these PCBs inside of there. I did the exact same process. I desoldered everything. I imaged the board. I reversed engineered it, schematic and PCB. The schematic was really interesting because, as far as I know, there are no schematics available for this board anywhere. It's not really known. It's not in the programmer's reference guide. I have never seen a schematic for it online at all. So I managed to recreate it, doing the BOM, doing the schematic. I recreated the PCB, not fully. I haven't done all of the finalized the board. I just pulled all of the signal traces to validate the schematic against. I will eventually come around and turn it into a full-fledged PCB as well. It's a fairly nice board. As I've been working on this as well, I've started running into the other unusual Commodore 128 versions. Jason Ewing found a 128D plastic, which held a revision-free PCB inside of it, which, after talking to Bill Hurd, he says that this is absolutely one of the original 1985 CES prototype machines, which is pretty cool. It's the underside of the board is full of budge wires, and interestingly enough for me, it was also missing the pull-up resistor for the dot clock. So somebody at some point at Commodore made the same mistake as I did on my board. Also, I gave this talk earlier at VCF East in April, and at that point I mentioned the Dreen Commodore 128. Dreen was an Argentinian company that was kind of remanufacturing and assembling Commodore machines locally in country due to some trade embargoes or tax reasons. I don't know exactly why. And the Dreen 64 is rather special because it has a PAL G VIC in it, which is unique. So I was always interested in trying to locate one of the Dreen 128s. I said at VCF East that there were so few of them sold that I don't hold any hope of ever seeing one. And right enough, I get contacted on Discord by a bloke named Tron, who gave me a whole bunch of pictures of one. So I've now seen one. We've established that it's a pure NTSC North American 128, just with a special badge on it, which is interesting, but not as interesting as one might hope. I'm still happy I managed to see one. Other things I've been working on is I recreated the PCB for the keyboard, because at least over here in Europe, a 128D might run you 150, 200 euros. A working keyboard for a 128D might run you about the same money. They're getting pretty rare. So I wanted to replicate the keyboard as well. I'm using mechanical key switches. I'm still working on the mechanical mounting and mechanical fit of it. But it's there, it's working. I had to design There are 3 locking keys on the original Commodore 128 board. So I designed a circuit to replicate that locking. So for all of those keys, it's right there. And all of this is up on GitHub as well. It's available right now, but I'm still working on the finalized fitting. So I'm getting prototypes for that as well in the coming week. And hopefully that should also be finished shortly. I've been using that as my daily driver on the 128 for half a year now. I don't want to use the original keyboards anymore. This is so much nicer. Ignore the keycaps. That was just the cheapest set of keycaps I could find on Amazon. So it's pretty nice. I like it. It has bees and cows on it. The pinout of this keyboard is matched 1-to-1 to the 128 CR. So that rather unusual board, which actually has a straight inline 25-pin header for the keyboard. Because I guess at some point, somebody at Commodore was realizing that the 25-pin header they were using for the keyboards was rather expensive. So the original Commodore 128 design has a D-sub-25 header or footprint for the keyboard connector. So you can mount a D-sub-25 for the 128D, the plastic. And to connect the keyboard on the wedge, they custom ordered a pin header with the same physical dimensions as a D-sub. And D-subs are not your standard 2.54 millimeters, so 0.1 inch, as you would expect to see. It's actually 2.77 millimeters. So finding pin headers for that is astonishingly hard, I discovered. I've been looking for it for a very, very long time. I found a company that will make me the pin header, but then I realized there's nobody that will make me the matching connector on the keyboard side. So I had to come up with another solution. And I decided to just replicate the design on the CR to be able to use a straight 25-pin connector. So it's on there. You can use a straight cable between the keyboard and the main board, and it just works. So that ended up fairly nice. So much of the 128, the 128 CR and the keyboard are available on my GitHub, which is github.com/jgrip, where you will find the KiCad files and Gerbers for most of these things. I'm not releasing the full C128Neo board. Instead, I have a replica called the Open 128, which is identical to the Revision 3.3 board I've been selling so far. So, but it's all there. I've seen people make boards from the Open 128 Gerber files, and they function as they should. So that's all fully open source now. Meanwhile, as I was working on all of this, I ended up buying a microscope to work on surface mount chips. And it was my first microscope. So of course I started getting curious. I've seen people look into silicon inside ICs. So I wanted to do the same myself. And I realized that there's a lot of nasty chemicals to remove the IC capsule. So the black epoxy that holds the silicon dye inside. The traditional solution for doing decapping is fuming red nitric acid at 60 degrees centigrade. Not something I want to play with at home in the kitchen, shall we say. So it's I was always a bit, I don't really want to start getting involved in this. And then eventually I found a video called Chips à la Antoine, where this man named Antoine goes through and shows how he decapsulates chips. What he does is he uses a hot air station set at 450, 500 C, heats up the capsule to the point where it gets really warm, at which point he discovered that the epoxy becomes brittle and you can crack it. So by doing this, you can actually crack the epoxy housing of the IC and get the dye out. Is really interesting. He has a video on YouTube called Chips à l'Antoine. So if you're interested in that, I would recommend looking that video up. It's pretty cool. If it has a bit of a knack to it, some chips can be trickier than others. I've tried doing it with a Yamaha chip, and that was just a nightmare. That epoxy would not let go whatsoever. Commodore chips are fairly simple to crack open and get things out of. So that's pretty nice. It saved me a lot of hassle in playing with chemicals, mostly. And of course, to practice, you just grab from the pile of broken Commodore chips. I'm pretty sure most of us have some dead CIAs and dead PLAs and those type of things. So I started looking at doing this, and I took some pictures. So the image on the left-hand side is the first picture I ever took of an IC. So that's a Commodore 128 PLA chip, 8721. And I was surprised with how much you could actually see on these chips, even with a fairly low-cost, low-magnification microscope that I had at that point. So I started looking at it, and there are small structures around each bonding pad. So the white squares on there represent the bonding pads where you have the bonding wires coming from the outside of the chip. And looking around the bonding pads, I started eventually figuring out that you have inputs and you have outputs. Outputs have large driver transistors on them, so a large structure to generate the current capability that you want to connect to the outside, whereas inputs really just have a thin ESD protection system. So by doing that and looking at the larger ring structures around the chip for the 5-volt and the ground, I managed to figure out which pins were what on the chip. And then understanding how a PLA works. So you have an AND array and an OR array, which are connected using what's called product terms. So the input goes into the AND array. The AND array connects, in this case, vertically down to the OR array, and the OR array connects to the output pins. That's basically the structure of a PLA chip. So I started looking into it. Of course, this was about as good as I could get with my existing microscope, so I bought a microscope. Now I'm starting to get a bit more serious. This is an Amscope metallurgical microscope. Of course, at this point, I found another rabbit hole to jump into, which was CNC hardware. Due to the magnification at this point, I needed to start taking multiple pictures to cover the surface area of the die. So I ended up building my own CNC hardware to motorize things and move it around. It's basically a small board using an ESP32 microcontroller with stepper sticks like you would have on a 3D printer, and a firmware called Fluid NC, which is really nice. I put a Raspberry high-quality camera on there. The microscope had a C-mount for the camera. So the Raspberry Pi camera, the new high-quality one, also has a C-mount, so that was a match really well made. And with that in place, I could take a lot better images all of a sudden. So now you can start seeing more structures inside of the chip. The left image is the full stack of everything inside of the silicon, and the right image is me having removed everything except the substrate. So the lowest layer, the actual silicon plate itself. A lot of the stack up in these is done using silicon dioxide, so glass. And to remove the glass, of course, the chemical you would want to use, the only chemical that will attack glass, is hydrofluoric acid, which is not exactly the nicest of things to do. And me living in the European Union, which can be a bit nanny state at times, I'm not allowed to actually buy hydrofluoric acid. But eventually I figured out that Armor Etch glass stainer has a 3% hydrofluoric acid solution inside of it as a cream, which works perfect for me. You can slab it on there, you let it sit there for a while, you rinse it off with acetone and water and IPA, and you can control the process with how much glass you want to take away. So on the right-hand image here, I've removed everything just to get a look at the diffusion layer down here. We'll go into that more in detail later on. But that allowed me to actually decode the logic of the of this PLA chip. It becomes even more obvious when you start looking at the OR matrix. So with the full matrix in place on the left side, it's really hard to see what's going on. Once I remove the metal and the polysilicon and everything else, and you're left with the substrate and the diffusion layer, you can start seeing the structures, and each of these structures here represent a transistor, which connects things. These small devices were called diffusion slugs, and this is how they programmed the PLA. It was done with the diffusion mask. So with all of that in place, you can sit down and spend a lot of time in figuring out where things are connected, which pins go to where on the whole matrix, input pins, output pins, and all of the various product terms going on the vertical. And with that in place, I made a spreadsheet. I kept track of all of these things and figured out what was connected. So here you can start seeing the actual logic of the PLA chip. If you understand the structure of the PLA chip, you can actually decode the logic that was put into this PLA. They have been doing the same level of decoding work also on the C64 PLA, which was a great help. There is a very fantastic PDF on this from Skue, who really goes through all of the various bits of the C64 PLA. So I did the same with the 128. I extracted all the logic. However, if I go back to the original image here, just below the OR gate, the OR matrix, there's a mystery block marked with a question mark. All the outputs were going into structures inside of this mystery block before they connected to the output pins. So if I wanted to fully understand the PLA chip, I needed to understand what this mystery block was doing to the things. So at this point, I needed to actually get an understanding of how ICs function. So far, it's mostly been me decoding it with just pure luck. You basically just assume that where this structure is in place, there's a 1. If it's not, it's a 0. So far, I've been able to decode everything by even with knowing nothing. Just like looking at a PCB, you can see where things are connected or not. To understand those mystery blocks, I had to actually understand chip manufacturing. After a lot of looking around, I managed to find this fantastic book, which is Introduction to VLSI Systems. It's written in the late 70s by Conway and Mead. As far as I've been told, it was also fairly common to find on Commodore chip designers' desks. So it's kind of the text on NMOS design from that era. This, of course, was yet another rabbit hole to jump into, understanding chip manufacturing and design and all of those type of things. Most of the things on the internet is all about CMOS, which was not very helpful for me to decode and understand this. CMOS is NMOS and PMOS at the same time, and the way you design logic is very different in those. I, of course, had never looked at any of this before, so this was all live and learn. But on the upside, I finally actually figured out and understood how a MOSFET transistor works. It's not just black magic anymore. I mostly understand the physical reasoning behind how it does what it does. So what you can do is you can look at a side cross section of one of these chips. So you have the substrate at the bottom, which is in this case p-doped. So you do doping, p-doping, and n-doping. I don't know the actual dopants they use to introduce it. I think boron is one of them. I'm not sure. But in NMOS, you have a p-doped substrate, and the source and drain are n-doped, and that's basically the diffusion areas that you see. You then have an insulation layer and the gate, which is polysilicon, so that's added later on. You have a single metal layer, which is represented by the blue, and then you have can have connections between the layers using vias or slugs. Those are also sputtered in there, and all of this structure is held in place with many layers of silicon dioxide. So it's glass as an insulator to keep all of the parts separated, which is laid on in various layers, which is not illustrated here. And then finally on top, they add a single layer of glass on top of everything they call the passivation layer to keep the oxygen away from disrupting the IC itself. Incidentally, this is why the C64 PLA is having so many issues. The passivation layer has a contamination problem. As far as I understood, the C64 PLA has boron contamination in the passivation layer, which allows oxygen to get into the rest of the chip and basically corrode it. Commodore, or well, MOS and later Commodore Semiconductor Group pretty much only ever did NMOS. I know they had a CMOS line for a very short for a short time to do some chips. I think related to the LCD panel manufacturing they had at some stage. But most of it was all NMOS. They called it HMOS and HMOS2. HMOS is an NMOS process, but done slightly differently. It's the same NMOS in essence. Commodore kept track of which chip was doing what. So if the chip ID, the 4-digit chip ID starts with a 6, it's going to be NMOS. If it's 7, it's HMOS, and if it's 8, it's an HMOS2. So most of the Amiga chips, for example, the original ECS and OCS would be HMOS2 because they're 8 blah 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 chips, 8722 on the Commodore 128, etc. The original 6502 is NMOS, etc. The feature size on this was 4 micrometers, but during the design feature size was 4 micrometers. But I had the great opportunity of speaking to Albert Charpentier, who was really one of the lead chip designers back then at Commodore, and he said that during the manufacturing process that actually shrunk to 3 micrometers. So that was basically how these chips were made. It's a fairly involved process manufacturing these, and I would say that manufacturing processes is as complicated, if not more, as it is to do the actual chip design itself. It's a different discipline, but both are really complicated. The more I learn, the more amazed I get. So how do you use all of this to actually make logic? Well, if we look at a single inverter, and now I'm talking NMOS here, CMOS or PMOS would look very different to this. You can basically consider a standard inverter gate like this on the left-hand side. If I were to make it with a MOSFET, you could possibly imagine a situation where you would have an NMOS MOSFET and a pull-up resistor, and this would basically generate an inverter. If there's no voltage on the input, the NMOS will not conduct, so the output will be connected through the pull-up to VCC, and you will get a 1. So 0 in, 1 out, and vice versa. If there is a 1 on the input, the NMOS will conduct and it will pull it down to ground, and you get a 0 out on the output. So Now, of course, how do you get a transistor into an IC? Sorry, not a transistor, a resistor inside of an IC. Well, you can use something called a depletion device. A depletion device is a depletion mode NMOS transistor where the source is connected to the gate. And you do it slightly differently. So the polysilicon, so the pink on these is polysilicon, and yellow is a contact hole, which allows it to make contact between layers, and green is diffusion. So I'm not going to go into too much detail on all of this, but when you see a wide polysilicon slug sitting on top of this with a contact hole on it, it basically is a very small resistor made out of an NMOS transistor. The input then has a polysilicon going across a diffusion, and that turns it into a transistor. And then ultimately on the rightmost side, you can see the same thing on an actual silicon die. That shot comes from a Commodore 128 MMU chip. I love that little section of the chip because it's such a fantastic textbook example of an NMOS inverter. It doesn't really get much better than this. So learning all of this, of course, allowed me to start decoding that input block, or sorry, the output block in the PLA chip. I took a picture of one of these blocks. I once again used my arm wrench to remove all of the layers so I could look at the diffusion part. And then I just sat down with Inkscape and replicated all of this in a vectorized format. So I just drew all of these with the layers, as you can see, in Inkscape to allow me to have a clean source to look at as I was working on it. And then it was just a matter of sitting down with pen and paper and converting this into a schematic, which I ended up doing. So I'm not going to go into all of the details here, but you can see in this area here, for example, you have two transistors. One is a depletion mode device, one is a transistor. So you have an inverter sitting right there. So being able to decode all of this, you can then use more normal gate symbols instead. And you end up with this schematic. And when I simplified it even more, I discovered that it's a D latch that's sitting on each of the output signals. Only two of them are connected and latching, which is DRAM write enable and the CAS enable, which is a signal that gates the CAS from reaching the RAMs. And with all of that in place, I could start writing Verilog. Well, really replicating the chip. There have been some attempts to decode the 128 PLA before, in the same manner as the first decodings of the C64 PLA. So the C64 PLA is entirely combinatorial. If you give it a set of inputs, it will always present the matching set of outputs. There's no state logic held inside for any reason whatsoever. So by just iterating through all the possible inputs, you can get all of the possible outputs on the combination, and from there you can basically deduce the logic by looking at it and reverse engineering it that way. This does not work on the Commodore 128 PLA because of these latches. There's state inside of there. It's a registered design instead of a pure combinatorial. So we literally had to take the chip apart to reverse engineer it to fully understand what was going on in there. With that in mind, I sat down and wrote some Verilog. I had no idea what Verilog was, so it was another rabbit hole to dive into, learning HDL languages and modern chip design, etc. It's been very useful since I've started playing with FPGAs and CPLDs, so it's been very, very useful. once again, this code is up on GitHub. It has been verified. I had machines running on these with replacement chips. Evie from Backbit is selling replacement PLAs based on this logic. And I think as Lapion has also been working on using these. So both of them have contributed fixes back as well. I made some mistakes when decoding in the matrix. So that was pretty encouraging, the fact that I actually managed to reverse one of the chips and have a computer work on it. So I did some debugging. This is really exaggerated. What I was doing here was I made a stacking tower to keep an original PLA and one of my replacement PLAs working at the same time. All the inputs are connected to both chips, but the outputs are separated. The original one goes back on the motherboard, and my replacement chip is just left hanging. And then I connected everything to a logic analyzer so I could validate that what I do as input, that I always get the same outputs as an original PLA. I also did this to be able to validate all of the timings. So the original chip, PLA chip, does propagation in 35 nanoseconds. So if you change the inputs, it will take 35 nanoseconds for the outputs to match its new state. Bill Hurd told me that they had a 40 nanosecond budget for this chip, so they met that one. Whereas my replacement PLA has a propagation delay of 6 nanoseconds. And to my amazement, the computer works fine, even with this much lower propagation delay. This has been a struggle with the C64 PLA. The C64 is a lot more timing sensitive on this. It does not like having too low latency on the PLA chip. It messes up the timings and it just loses stability. So this was really a fantastic setup. Working on this, of course, I ended up buying yet another microscope because now the bug has bitten me. So this time I went proper serious. I bought an old Olympus metallurgical model. I motorized it. I can't spell apparently. So I motorized this one as well on my own. I'm using a DSLR camera instead of the Raspberry Pi. I learned a lot more about how optics works, which was yet another rabbit hole. I've had so much fun doing this because I've found so many things I've been learning and studying up on. So the goal of this one is I motorized the Z-axis to allow me to start playing with something called focus stacking. So when you are at really high magnifications, as you do when you take these images, the focal depth of the camera becomes really, really low, to the point where if I take sharp images of the of the substrate, the other layers are blurry. If I focus on the polysilicon, the metal is blurry and the substrate is blurry, etc., because it's a 3D stack, right? So the latest rabbit hole I'm now dug into is taking pictures, the same picture as varying focus depth. So make the substrate focused, make the polysilicon focused, make the metal focused, and then messing around with OpenCV to do focus stacking in software, which will allow me to basically make an image of the silicon that is sharp all the way through. All the layers are sharp in one image. So that's my current playground that I'm messing around with. It's really interesting. I've also starting to collect up quite a few requests on imaging chips. I did take apart an image, the BBU chip out of a Mac SE, which people have looked at reverse engineering the logic out of as well. We've also dug up a special chip for the BBU, so it's a BBU replacement from a company called Brainstorm. which is a turbo BBU for these. So we're looking at replicating that chip as well. It's all rather interesting. And I needed a better camera to do all of this work. So yeah. Future plans for all of this is I want to finish re-implementing the MMU. So I'm taking some images. I'm working on writing Verilog from both the datasheet and from some of the reverse engineering I've been doing. I'm getting fairly close to also having the MMU chip replicated, which brings it down to the VDC left. All the other chips in this computer, you can either buy new, or there are existing replications either available or on the way. So the CIAs, there are 3 projects I'm aware of that's working on replicating the CIA chips. You have the VIC-2 Cavari chip going on that will eventually replace the VIC-2 with an FPGA. I've done the PLA. The Z80 you can buy brand new. 8502 is a 6502 with the same I/O registers as 6510, just with 2 extra pins compared to the 6510. So there are various options available for replacing that one as well, on its way or already out. And the SID, of course, there's plenty of SID variants and replicas for whatever you need. So that pretty much leaves the PLA, the MMU, and the VDC as uniquely Commodore 128 specific chips. I've done the PLA, I'm working on the MMU, and then I will tackle the VDC chip with the ultimate goal of trying to be able to build a brand new Commodore 128 using only new parts. Which of course is the ultimate goal for a preservation effort. I could do this inside of a single FPGA, like the Ultimate 64, for example, which is a nice approach, and I wouldn't be entirely against it, but my personal preference lies in the lines of having a data bus I can put my finger on. I really like having separate individual an MPU, I/O chips, a video chip, etc. on the board. It's my personal preference. So, and yeah, that's where I'm at right now, and that's pretty much me for this talk. Any questions? I'm happy to answer at this point. I hope I haven't bored you all to death already.
Which FPGAs do you use? Use the Xilinx ones or some other ones?
Once again, I'm following the same theme as with the PCB software. I prefer things where I can do open source as much as possible. So right now, I've mostly been messing around using Lattice ICE 40s.
Oh yeah, I saw some of those, but they weren't available to order or something. They were like, you have to wait 6 months.
That is correct, but I bought a bunch before we ran into the big issues.
Okay.
I have some. The nice advantage of those is, of course, you have the whole YOSYS suite of open source software for them, which makes it really fantastic for me. I'm thinking about having a look at the GoWin FPGAs that are out on the market now, because they are still available, surprisingly enough.
Yeah, I did an Apple II and using the Xilinx Vivato. It's real easy. I mean, the tools are free and you can get the FPGA boards.
Yeah.
So anyway, that's great talk.
Yeah, thanks.
Hi, Johan. Robert Bernardo here. I saw you at VCF East, and I was hoping you would be over here at VCF West, but you're not. You're all the way back in Europe, I guess.
Yes, I'm at home in Luxembourg. It was a bit too much to travel.
Okay, I have a question. Okay, so I looked for C128Neo boards for sale online, and I did not see any red boards. I did not see any green boards. However, I saw black boards that were being sold from Canada. What version are those black boards being sold from Canada?
That is Core i64. He's been acting as a reseller for me. Those are the revision 3.3 boards, which has been the main bulk of all the boards I've sold. They do have that one issue with the dot clock resistor being missing. But aside from that, they are officially sanctioned board and of the revision I've been selling.
Oh, very good, because I wanted to direct people toward, an official reseller, and I guess he's the one.
And what I will say is, if there are no showstoppers on the revision 4 boards that I will receive this week, so I will build one and test it this coming week. If there are no showstoppers on that, I will start selling revision 4 boards as well.
And those would be through ICOMP also in Canada? Or I'm sorry, I'm using the wrong term.
I sell on Tindy myself.
Oh, yourself. So what is how do we contact you then if we wanted to buy directly from you?
The easiest way, you find all the links and all of the assembly information, the bill of materials, the component placement files and everything else on C128.se.
Okay, very good. Thank you very much.
Even though I live in Luxembourg, I'm from Sweden originally. So.
Okay, thanks.
Yeah, my name's David Simpson. I'm curious on your latest camera setup, if that with that DSLR, is that giving you the ability to go through and reverse engineer to the point where you no longer need to use the asset? Do you get enough resolution?
The resolution is ultimately limited by the optical resolution of the objective primarily. So. When I'm using my 10x objective, so you have 10x in the objective and you have 10x built into the microscope system itself. So I end up with 100x, so either 100x or 200x. If I calculate the optical resolution I have in that optical path, not even talking about the camera at this point, I end up with needing approximately 4.5 megapixels in total. Anything above 4.5 megapixels will take of the same optical resolution, in essence. It's still advantageous to take pictures at larger megapixels, of course, because you can then bin. It does help with resolution, but you're ultimately limited by the optical resolution of the microscope itself. The output on the Olympus, and this is one of the reasons I wanted to buy a bigger one, the camera tube is 28 millimeters in diameter, and it's infinity corrected. So you basically have an image 28 millimeters in diameter coming out of the photo tube that's focused on infinity. So compare that to the AM scope I had previous, which is 180 millimeter focus, so you need to have the camera mounted at the exact correct distance, and you also have a lot more braking in there, so you get much heavier vignetting on that setup compared to the one I have now. It's also very helpful having the DSLR. I'm using Sony Alpha cameras primarily because they are mirrorless and you can run them in shutterless mode, which means I don't get any vibrations in the entire microscope stack by taking a picture. They additionally also very helpfully have HDMI output where I can remove all of the camera status from that output. So I can actually just use an HDMI capture card and capture images that way instead of taking pictures, which helps speed up the process immensely. What's hard to get through in a presentation like this is this has been 3.5 years in total of my life, messing around with this, learning things about microscopes and silicon manufacturing and PCB design and everything else. So it's all been going in parallel and learning, etc. I've been incredibly lucky buying the right things for the microscopes over time. And, in case of any questions after all of this, I'm also available on the VCF Discord server and some other places. It's all the places I'm at is also linked on C128, Yeah.
Okay, thank you, Johan. We're wrapping it up.
Yep. Sounds like a plan. Thanks for having me.